So we talked about vertical asymptotes and we talked about horizontal asymptotes. The last type of asymptote that might appear in a rational function is called a slant asymptote. So a slant asymptote, what's going to happen to find this is we're going to look at the degree of the numerator and the denominator. So just like with horizontal asymptotes, we look at the degree of the numerator, the degree of the denominator. Now, in the case that the degree of the numerator is 1 larger than the degree of the denominator, so it has to be exactly 1 larger, there will be a slant asymptote. Now remember, when the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. So if it happens to be 1 larger, there is no horizontal asymptote, but there is a slant asymptote. If it's 2 or 3 or 4 larger, then there's no horizontal asymptote, there's no slant asymptote. So this is just a special case of when there is no horizontal asymptote, there might be a slant. So here is the example that we looked at last time of a rational function where the degree of the numerator was larger than the degree of the denominator, but in this case, the degree is 1 larger. This is 2, this is 1, so here we have a slant asymptote. So what a slant asymptote is this is going to be this line that our function seems to be approaching as we go off to infinity and negative infinity. So as we're going off to the sides, this seems to be getting closer and closer to some type of line. So if we look at this line, it looks kind of like the following. Right? It looks like maybe this is getting closer and this is getting closer. If you graph this on your graphing calculator, you will see very clearly, if you zoom out a lot, that these do seem to be getting very close to a straight line as the graph goes off to the sides. So to find out what is the equation of this line, of the slant asymptote, we're going to have to do division. Now again, you can either use synthetic division or long division depending on the type of expression you're given. But once we do division, y equals the quotient. So whatever the quotient is, that's going to form our slant asymptote. The remainder plays no role in this. We're not concerned about that. It's only the quotient. And so if we take a look at this example, if we do x squared divided by x plus 1, we do the division. We could do synthetic division because we're dividing by a degree 1 polynomial where the coefficient of x is 1. We can put negative 1 in our little box here. And then we put down powers of x's. Or we put down the coefficients of x's. So the coefficient of x squared is 1. But remember, we have to include all of them. We have to include all of the powers of x's as they decrease. So the coefficients of those missing powers are both 0. So the coefficient of x squared is 1, coefficient of x is 0, coefficient of the constant is also 0. So now we set up our synthetic division, bring down the first number. I multiply to get negative 1. I add to get negative 1. I multiply here to get 1. I add to get 1. Now remember, this last number is our remainder. These form our quotient. And their degree 1 less than what we divided by, this will always be a line, basically. So always think that this is just the equation of a line with the coefficients. So my quotient in this case is x minus 1. Coefficient of x is 1, the coefficient of the constant is negative 1. So this says that y is equal to x minus 1. This here is my slant asymptote. And if we look on the graph over here, we see that's about what we have, that this line has a y-intercept of negative 1 and has a slope of positive 1. So that seems to match with what our graph looks like. And so that's how we find the equation of a slant asymptote. If it exists, based off of the numerator having a degree 1 higher than the denominator, we do our division, take the quotient, and that is how we find our slant asymptote.